What's up, everybody? How are you doing? Today's live is a fun one. We're talking about electrochemistry. Now, electrochemistry is how we make electricity using chemicals. It's in the name, right? But there's a lot that goes into electrochemistry, and it is important, especially in today's world, because guess what? Your cell phone, your car, um, even a lot of appliances at home are using electrochemistry. So you should have seen this in your lecture, but we're going to talk about a little bit of a recap before we get into today's experiment. And today's experiment is a pretty fun one as well. I'm pretty excited about it. But let's give a quick recap of electrochemistry and redox reactions. So when we talk about redox reactions, we're talking about reduction and oxidation. That's where redox comes from. Now, oxidation is the loss of an electron, right? Oxidation is the loss of an electron, and then reduction is the gain of an electron. So these redox reactions, by the way, they not only happen in batteries, they happen a lot in your body. I'm a biochemist and we do a lot of biochemical reactions, and a lot of them, especially the ones that give out energy, are redox reactions. Right? So one entity loses an electron and then another entity gains an electron. So one undergoes oxidation, the one that loses an electron, and then another one that gains an electron undergoes reduction, right? Now, a lot of students get confused, so I added this here to kind of help you understand these terms, right? So stay with me here, right? So something that undergoes oxidation, meaning something that loses electrons, is oxidized. So far, so good. However, we call it a reducing agent, right? So three terms. Something that undergoes oxidation is going to be oxidized, and then it's going to be called a reducing agent. Why is it a reducing agent? Because it is going to reduce this other compound, right? So the compound that undergoes reduction is going to be reduced, and we call it an oxidizing agent. So this is where a lot of people get confused. If something is an oxidizing agent, it undergoes reduction and it is reduced. And if something is a reducing agent, it undergoes oxidation and it is oxidized. So make sure that you understand these terms. But all we're saying is that, let me give you an example. Let's see if this is going to work. So if we take something like, no, let's say we take copper, right? Copper plus zinc sulfate, right? And it gives you, make this smaller. I wonder if I can do this. Oh, yes. Okay. All right. Move it too. All right. So copper plus zinc sulfate is equal to zinc plus copper sulfate. If you all remember, this is what we call a single replacement reaction, right? But as you can tell, right, copper goes from copper by itself to copper 2 plus. So it loses 2 electrons. And zinc goes from zinc 2 plus to zinc. So it gains the 2 electrons. And guess what? These two electrons are the electrons that come from copper. So which one is oxidized? Well, copper loses electrons, so it is oxidized. And zinc gains electrons, so it is reduced. So if zinc is reduced, is it a reducing agent or oxidizing agent? It is an oxidizing agent, right? So again, this happens a lot in nature, in our bodies, but today we are talking about it in terms of a an electrochemical cell or a battery. What do I mean by that? If we go here, something we call a galvanic cell or an electrochemical cell, right? So these types of cells are cells where you can have these reduction and oxidation reactions. And the reason why we're doing this, guys, okay, so going back to this example that I just gave you, right? If you look at this example, where is my example? Where did it go? Hmm. Mm, I don't know, but if you go, let's look at this example here. Actually, we can do this. Okay, so if you look at this example, you see that again, zinc here, zinc lost electrons, and then copper gained these electrons, right? So this is a movement of reaction from one place to another. But guess what? Electricity is the movement of electrons. That's the definition of electricity. When electrons move, you create electricity. So you can intercept the movement of these electrons, and then you can add a light bulb here. You can add a voltmeter. And then when you do it really well, you can actually have a cell phone, power a cell phone or something like that, right? So this oxidation happens at a place called an anode, right? This is one side of this electrochemical cell, and then reduction happens at the cathode, right? Anode is the negative terminal, the cathode is a positive terminal. All right, everybody with me? Galvanic cell or electrochemical cell is a cell in which a redox reaction happens, and the movement from that is used to produce electricity. And it has two cells, an anode and a cathode. And at the anode, you have oxidation, at the cathode, you have reduction. And these are separate, right? And in here, right, as you can see, you have zinc sulfate in the solution, but you also have a zinc metal here, right? So you have zinc sulfate in the metal. Zinc sulfate is the one that's going to give us zinc 2 plus ions, and then you have the metal here. And guess what? On the other side, you have copper, and then you have copper sulfate, the copper metal, and then copper sulfate accounting for this reaction, right? And then you connect them with what we call a salt bridge, right? To connect the current. This salt bridge here is KCl, but you can use another chemical as well. And guess what? This is what we're going to be doing in this lab. We're going to be doing this, but we're going to make it a little bit more fun. But before I get there, let's look at a little bit of more about chemistry. Because think about this, right? Think about it. If I give you copper and zinc, right? Which one is going to give away its electrons? Which one is going to gain its electrons? How do you figure out which one is going to give away, which one is going to be gaining? Which one is going to undergo reduction? Which one is going to undergo oxidation? Very important. So we have these, we call them standard reduction. So every metal out there, we already have data. So this is a nice table from your book that talks about reduction potentials, right? Every one of these has reduction potentials. So if you want to, for like copper and zinc, if you want to see which one is going to undergo reduction, is the one that has the highest reduction potential. So let's see here, you can see zinc has a reduction potential of 0.7, negative 0.76, and then you go back to see if you can find copper here. Um, Copper is plus 0.34, right? So copper is bigger than zinc, right? So then copper is going to undergo reduction, zinc is going to undergo oxidation. That's how you know. So you look at these, you're like, oh, okay, that's why copper gained electrons, zinc lost electrons. The half cell with the highest reduction potential undergoes reduction. So then, now that we know which one undergoes reduction, which one undergoes oxidation, you can then go to the next step where you can find these potentials, bring these potentials, and more importantly, this is actually a very important point. How do we measure the reduction potential of the cell? We combine these two. But when we combine these two, if we go back, we saw that zinc is negative 7.6. But the negative 7.6 for zinc, right? If you look into it, the negative 7.6 for zinc is for the reduction of zinc. This is a reduction potential, right? But if you go back to what happens to zinc here in our real reaction, zinc is going to be oxidized. So it's the opposite. That's why when you come here, for zinc, it's plus 0.76. And then when you add them together, you should be able to give me the full reaction, right? And the full reduction potential, making sure that the electrons are equal so that we can cancel them out. If they are not equal, we're going to have to multiply one or the other, right? So make sure that you can measure reduction potential. This is the most important calculation of this lab, of this chapter, of this subject, being able to measure the potential, to calculate the potential. Why does it matter, by the way? Because this is how you're going to learn about what type of electricity you're going to learn how to you're going to produce. This is the potential. The potential measures electricity. So if you go back to this, you're going to add a voltmeter. This voltmeter measures the potential. Very important, right? Now, the one calculation you're going to have to know how to do is the potential. The number two calculation that you're going to learn how to do after you know the potential is what we call delta G, right? The free energy of the reaction, the energy of the reaction. You're going to take N, which is the number of electrons, times F, which is the Faraday constant. Then you add the potential that you calculated above. That's how you calculate delta G of the reaction. And from delta G, you can be able to tell whether a reaction is spontaneous or not. And the number three thing that you can calculate from this is KAQ, which is the constant, right? If you remember the constant is K, right? K is, so if you already found, look, if you can find the electron potential from measuring it, right? You can, or from calculating it, you can convert the potential into delta G, which is negative NFE. And then guess what? After you got delta G and the potential, you can actually find K, which is the equilibrium constant of our reaction. So you can find the potential, the energy, and the equilibrium constant by just measuring or calculating the potential. And you're going to be doing this, right? So we are going to do that. And again, if something has a negative delta G, it's spontaneous. If it has a positive delta G, it's non-spontaneous. So you should be able to tell. All right. So that is what we're going to be doing, guys. That's what we're going to be doing. And how are we going to be doing it? We're going to be doing it by setting up a reaction like this. We're setting up a reaction like this. but we're going to use these special tools that we've used that we've made. But it's the same idea. You have a a cell here, you have another cell, then you have something to connect them, and then you have these electrodes, and then you're going to measure them with a voltmeter. So we are going to do these, and we're not only going to do this for just two chemicals or two metals. We're going to do this for like four different, I think six different combinations. So it's going to be pretty cool. So the way they're going to look like is we have these boxes, right? We've made these boxes. We actually designed them. We're trying to see if we can publish them, but we designed these boxes to be able to do what we're trying to do. So the way these boxes work is instead of having bakers. So it used to be like a tedious bakers where we used to use a lot of chemicals and all that stuff, and the metals here will be falling. So it was kind of a very hard experiment to do. But here, the way we're going to do it is you have a you have one cell on this side connected to another cell on this side, right? Pretty cool. So they're going to look like this. We're going to pour the solution on one side, pour the solution on another side, and then pour the salt bridge solution, the solution that's going to connect them in the middle, right? And then we're going to we add a filter paper on this side to connect them. Again, going back to what we have here, we are following this, right? So we're going to add a filter, a wet filter paper that I'm going to send you, right? So that you can connect them. And guess what? You're going to bring in the metals and then you put them here. So we added little hooks or little holes where you're going to be adding the metals. So they can hold the metals, and the metal is going to actually be standing up rather than just falling down like we used to when we used to use beakers. So these, we are very proud of these. We are still testing them, but so far they have worked much better than we anticipated. And not only can we do this, this system allows us to use more than one, more than just two. So this can come in and connect in here, right? Like that, boom, and then now you have another cell, right? So it's going to be really good. I think for this lab we are going to use four of them, right? So looking at your manual here, let's see. Yep. So we have a few combinations, right? If you look at here, we're gonna have a few combinations, right? So you can have like three, you can have six, you can have four. So for this one, you should have zinc, copper, nickel, and then maybe tin. That way you can like make different combinations, and then after different combinations, you're going to be putting your data in here. So you can have like zinc and copper, nickel and copper, tin and zinc, tin and nickel, tin and copper. So for the four that I gave you, you can actually have like six combinations, right? If you add two more and then you have six, you can have a lot more combinations, right? So so I gave you a table for the ones that I gave you, and then I'm going to give you the half reaction, right? The standard of half reactions, so that you can use them. These are reduction potential of half reactions. You can use them to calculate. So you're going to calculate the voltage here, and then you're going to calculate to measure the voltage, right? So we're going to calculate the voltage, then measure the voltage, and then we're going to compare our data, right? But in addition to that, we're going to be, like I said, we're going to be calculating the delta G and the KEQ of our solutions as well, right? So I think that's enough for you to understand um, the galvanic cell, a very important, very crucial chemistry component that we use every day, right? In order to, in batteries and things like that. But again, it's way more common than that because our bodies, our cells use them. They are using them right now. If you ever heard of like, glycolysis or citric acid cycle and all that stuff, things that our cells are doing to produce energy right now, they are full of redox reactions. Another fun thing, we're not going to be able to do this today, but you can have the opposite. Instead of having a galvanic or electrochemical cell, you can have something we call electrolysis, right? Which is instead of using a chemical reaction to produce electricity, you're using electricity to actually produce a chemical reaction. So you can use electricity, for example, to break down water into hydrogen and oxygen. So we call it electrolysis, or an electrolytic cell is the opposite of an electrochemical or galvanic cell. But that is enough. I'm not going to talk about it, but if somebody mentions it, make sure that it's also part of electrochemistry. But today we are going to be building galvanic or electrolytic cell. And the way we're going to do it, we're not going to be using this traditional method. We're going to be using this component. We're going to do a bunch of reactions here, and we are going to compare our calculated voltages to our measured voltages to see whether or not they agree. But other than that, I think you're ready to get started with the experimental portion. If not, feel free to reach out and ask any questions. But let's get started.
For this lab, you're gonna set up electrochemical cells as discussed in the intro. Now, the way you set them up is going to be based on these hexagonal boxes that you have in your kit. And it will depend on how many electrodes you have and which electrodes you have. So if you have 4 electrodes, which most of you will, you can have like, oh, I have zinc, I have tin, I have copper, I have nickel, and that will be your electrodes. And the middle here, as we learned, is our bridge. This is our salt bridge. But guess what? If you have 3, you can do a 3 electrode setup as well. If you have 6, you can do a 6 electrode setup. We love this kit. And then after you set them up, you should have all these solutions. So step 1 is going to be connecting these boxes. Step 2 is going to be pouring the solutions in each of them, and then step 3 is going to be add electrodes. So if you have a zinc solution, you have a zinc electrode, copper solution, copper electrode, nickel and tin, and so on and so forth, right? You're going to add it because these hexagonal boxes have a nice space in here where you can add electrodes. We designed it so that everything you need is right there. Okay, so after you set them up, then you're already done. What's left is reading the voltage between the 4 electrodes, right? So let's scroll down to this table right here of voltage, right? So now, depending on what you have, you will not fill out all of this table, right? This table assumes that you have all of the electrodes, but you probably won't have aluminum. You might not have some of these. You might not have iron. So if you have only 4, only fulfill the ones that you have. But as you can see here, you have the half reactions, and that's what you're gonna use to do what? To calculate the voltage of the cell. And then after that, we're going to measure the voltage in real life using these boxes, and then we're going to compare the calculated versus the experimental voltage, right? Let me bring it down so that you can see it. There you go. Calculated voltage, experimental voltage, half reaction, and then another half reaction, right? So this is the table that you're going to be filling out, but again, you will not fill all of it out because you won't have all of the electrodes. Now, before we get started, of course, you're going to have your goggles and gloves as always, but on top of that, you should have your tables so that you can record your data, right? And then after that, you should have the solutions, and then you should have a voltmeter, and then you should have these filter papers that we gave you, and these will be your bridges. Why do we care about bridges? Is because going back here on our setup, there you go. All right, so going back on this setup, these solutions need to be connected by a bridge, right? Because remember, we are measuring the transfer of electrons. So for this one, it's very easy. We just weight this filter paper by our solution KNO3. So this is our salt bridge, right? So that's why we need those filter papers, and you should have plenty, but make sure that you have those. If you don't have those, you won't be able to perform the experiment. We also have, of course, goggles and gloves. You're going to have a voltmeter that's going to measure the voltage, and then you're going to have metal electrodes, and then finally you should have your solutions, right? So again, the boxes, the bridge, the voltmeter, the metal electrodes, safety, and then your solutions. All right, after you have everything, then you are ready to get started. All right, so how do we get started? We are going to start by calculating the voltage, right? Start by calculating the voltage needed, right? It's very important that you calculate the voltage based on the techniques that we learned, and then from there we can actually measure the experimental after we have the theoretical, right? So take time to measure all the voltage on the table, and then after you're done, put on your goggles and gloves, right? Safety first, right? And then the first thing you're going to do is you set up your boxes, right? And again, we're probably going to have 4 electrodes, so you're going to set up your boxes like I showed you in this way. You have 4 boxes around, and then after you set up your 4 boxes, you're going to add the appropriate metals, right? So you add copper, you add zinc, or whatever other metals you have, and then after you add the metals, you're going to pour the solutions in the appropriate metals. So for example, what Bryson has there is copper sulfate, and the copper sulfate is gonna go with the copper electrode, right? Very straightforward, but very important that you match them, right? So we are trying to match these. All right, so going to add the metal, and then in the middle you add the salt bridge that's going to join them. And then after that, what we're going to do is here is, if you added too much, you can take off somehow, but so we're going to weight our paper towers or filter paper. Those filter paper, the tiny strips of filter paper, we're going to weight them by the solution in the middle, right? We're going to weight them, make sure that they are weight, because they need to be able to transfer electrons, so that's why we're making them weight. And then after that, we're going to join all of them. So we're going to join all of the reactions with filter paper, right? This is an important distinction. All of the reactions need to be joined by filter paper. I don't have a good top-down shot, but basically what you're going to do is you're going to add filter paper. You're going to add filter paper here, filter paper here, filter paper here, filter paper here. You're going to join all solutions by filter paper. Very important, right? And then once we make a good connection, then that means that everything is connected. So now we're ready to measure the voltage, because now the electrons are moving. So we can measure the voltage, which is the movement of electrons, which is electricity. So you turn on your voltmeter. You should turn on your voltmeter, move it to where you're able to find a a good range of expected voltage. And then all you're gonna do is just put the two tips on two metals. Put the two tips on two metals, make sure that it's stable, read the voltage, and that's it. You don't even have to attach it. Just make sure that both of them are touching. You should get a stable number, and then guess what? You record that number. Where do you record it? In the table that we have. So going back to our menu, I have a nice table here that you're going to be recording the experimental voltage right next to the calculated voltage. Right, so record and then go to the next, record, go to the next. So this should be very quick after you have it set up. So record all of them, right? Record all of the combinations, and then after you're done with all the combinations, you're pretty much done, right? So after you're done, right, make sure you double check your readings and all that stuff. If your reading is way off the expected, first double check your math and then double check your reading, just to make sure that there is no error. And then after you're done, you can just go ahead and start getting rid of the stuff, right? So you're going to clean off the metals, right? Clean off the metal electrodes. Make sure that you dry them off, right? Clean them off, dry them off. And then after you dry off the metal electrodes, you're gonna get rid of our reactions. You can get rid of them in the sink as long as you follow them with water. Make sure that you wash the boxes, right? Wash out everything. Some of these reactions are corrosive, so make sure that you wash out everything. Make sure that everything is clean, and make sure that you don't touch any of it. And then after that, you just clean up your area, let it dry, package it well, and then you are done with the experiment.
That is it, guys. That's electrochemistry lab. I hope you enjoyed it. I hope you learned something today. And make sure that you clean up well. You write down your data. Make sure that you do your pre-lab, your post-lab. And if you have any questions, as usual, feel free to reach out. And I'll see you in the next one. Bye-bye.